Okay, let's take a look at Kirchhoff's rules. Kirchhoff's rules actually really are self-evident. There's really no reason why they should probably be associated with this one person because they're obvious and logical, the rules that we really basically already know. So the first rule that Kirchhoff stated was that the change in voltage around a circuit is equal to zero. And the reason for that is because essentially a circuit represents a closed system in which no energy can come in or out. So whatever is happening throughout the circuit, the increase or decrease in the potential energy of the charges, in the end it has to add up to zero. So if, for example, we had a simple circuit with a battery and one resistor, as the current passes through the battery, the voltage is increased because chemical energy is released that is gathered by the electrons, and when they exit out of the positive end of the battery, they have more energy than they left with. They move around through the circuit with no resistance, so nothing is happening to that potential energy, and when it passes through the resistor uses all of that potential energy. And if it wasn't like that, so let's say this thing came out at 12 volts and came around and it only dropped by 10. Okay, well now it's at 2 volts still, so when it comes back to the battery, now it'll be at a 14. And when it comes back around the next time, it'll be at 16, at 18. It'll just continue to increase in voltage. Right? That's like not a possible situation because that violates the law of conservation of energy. So this is something that should be hopefully fairly self-evident at this point, that anything that refers to voltage is going to be guided by the law of conservation of energy, because that law says that you cannot create or destroy energy. So once energy is closed in that system, it cannot come in or out. And therefore, if we start at any point around a circuit and we follow around, so let's say here at this point we would be at 0 volts, we'll jump up to the voltage of the battery, and let's say that's 12 volts. We come around here, we drop down by 12 volts. So now I'm back to 0. I'm staying at 0. I return back to the same position. I'm at the same voltage at 0 where I started. If I pick a point right here, I would be at 12 volts. So as I move around, I drop down. Now I'm at 0 volts. I come around, I go right back up to 12 volts, and when I return, I'm right back to where I started from. So there is no gain or loss in energy in a given point in a circuit. So if we start somewhere and move around through a loop and return back to the same position, we should find that all the voltages add up to 0. Okay, the second rule is that the current in has to be equal to the current out. And what that is referring to is, let's imagine that we have a parallel circuit now. And so we have current doing this. The current is going to branch. And so I can see at this point right here, this is a junction, that there are some currents coming in, some currents are going out. So I see one current that comes in from the left, I see two currents going out, one to the right and one that's going down this way. So what this is simply saying is that, let's say that 20 amps came in here, it could have gone 10 and 10, could have gone 19 and 1, could have gone 15 and 5. Any combination is fine, but the 20 amps that came in, it must be accounted for. It has to be somewhere. So there's only two options. It has to be in these two paths. So the combination of these two currents must be equal to what came in, and that is by conservation of charge, right? So these are our two big laws, the two most fundamental laws in the universe, and they keep coming up over and over again as we look at electrostatic force and electric field, and now with electricity and with more complex circuits, that conservation of energy and conservation of charge are constantly guiding everything that's happening in the circuit. So let's take a look at what a real circuit would look like. And these rules are fairly self-evident, but let's take a look at what does it look like in practice when you actually solve a problem using Kirchhoff's rules. Like, how does it actually work? So in order to do that, let's make an example. And I'm going to draw the circuit right here. So this is going to be what's really going to be especially more complex about this circuit is that we'll have more than one battery. Now, This may seem kind of weird why we would have two batteries in this system and they're not next to each other. You know, normally we would add the two batteries together like this, but this is actually how like a rechargeable system would work. So for example, we may have 120 volts on this side and 5 volts on this side. I'm going to make it a little bit smaller than that. We'll just do 12 volts on this side. But essentially, another power source can be used to force the current to go backwards through a battery in order for it to be recharged. I mean, that's how the rechargeable batteries work. The current must be reversed through them, and that reverses the chemical reaction and stores the energy back in the form of chemical energy so that it can be re-released again the next time that you want to reuse that battery. So let's give these guys some numbers so we can actually work things out here. This guy is going to be 12 volts. We'll say this guy is 5. And then we'll just use the same 5, 10, and 15 ohm resistors that we used before. So this guy will make 10 ohms. This guy will be 15. And we'll make this guy 5. Okay. So here's one of the basic premises that we have to recognize about this. When there's certain conventions about the way that we think about the voltage increase or decrease. So the way that's going to work is in the direction of the current. Oops. In the direction of the current. In the resistors, those are a voltage drop. Or that is to say that they are negative. But when you pass through a battery, so if you're following the current, just like I drew the current up here, if you follow the current through this resistor, then as you move from this point to this point, you would say that's a negative voltage or a voltage drop. The voltage is going to decrease as this device uses up some of the energy that was in those free charges. For the battery, the voltage increase. Okay, in the direction of the current. Now, you don't have to follow the current. Now, this again, I'm not saying that the current is actually changing direction. I'm just simply saying I could go in the other direction. I could say, well, I don't want to go around the loop in this direction. I want to go in the loop in the counterclockwise direction. So let me go through this way. Well, what do you do if you say the current is going in this direction? Then what do you say about this? Well, that would be a voltage increase, right? Because if the current really is going this way, that means when it exits out of this resistor, it's at a lower voltage here than it is here. So if I go from this point of low voltage to this point of high voltage, I'm increasing the voltage. And so when I put that into the equation, I would say plus this resistance times his current, because realize that's what the voltage would be. That's how you calculate the voltage of a resistor, is you multiply its current times its resistance. So I will put if I'm following in a direction that I'm saying is opposite to the direction of the current that I believe is flowing in there, then I'm going to say that is a positive voltage increase rather than saying a voltage drop. So the rules for batteries are they increase when you go with the current, and resistors you have a decrease. That should make sense then. If you go backwards, so opposite to the current, then for the resistors, that would be a voltage increase. And then for, obviously, logically, we would conclude that the battery would be a voltage drop. Now, I'm not saying the voltage actually drops going through a battery, because the voltage definitely increases, but if you're following the circuit, right, through this loop, which is what you have to do to apply the voltage rule, you have to follow through a loop, then you're going to use this rule, that the voltage will drop if we are moving in a direction that we believe is in the opposite direction to the direction of the current. Now here's the problem. How do we know which direction the current is going? You know, there's sometimes, you know, pretty obvious because of the way the batteries are set up as to which way the current is likely to be going. I would say the current is likely to be going in this direction, out of this battery and through this resistor, just like the current would go out of this battery and travel through this resistor. And then most likely they merge right here and travel this way. And then they'll split up again to go back to their individual resistors. And that's probably the way the current is going. But here's the thing that's great about Kirchhoff's rules, and that is that even if we messed up, even if it turns out that the current actually went through this resistor and backwards through this battery, that might seem odd, but again, that's how a rechargeable battery would work, is that it would be connected in a circuit that would force the current to flow in the backwards direction. That even though this guy has a voltage and he's trying to push the current in this direction, if you push hard enough in the opposite direction, of course, you can force the current to go backwards through the battery. And this would only be for a rechargeable battery. You don't want to do those with the regular alkaline batteries because the battery will catch on fire. It's not designed to do that. So be careful about doing this in the real world. So using these rules, we're now going to set up a couple of equations that are going to allow us to solve this. Now, if you think about it, right now I have three currents that I don't know. Here's I1, here's I2, and what I believe happened was that I1 and I2 came together and they formed I3. So I have three unknown currents. I don't know any of those currents. And so therefore what I will need is three equations. Now one equation is going to be really easy because obviously I have this junction. And at this junction, I know that I1 plus I2 would be equal to I3. Okay, so one equation down. Now, that's basically it because I don't have any other junctions. The other junction over here is just exactly the same thing. It's going to say I3 is equal to I1 plus I2. So that's not genuinely a new equation. So now what I'll have to do is start creating some equations by following through some of these loops. And I basically have three options. I can take the left loop, I could follow the right loop, or I could follow the entire loop. I could also go in any direction that I want. So I can go in the clockwise direction or I can go in the counterclockwise direction. Now normally, to my mind, I generally feel like I want to go in the direction that I picked these currents. I wrote these arrows. They weren't given to me. I had to guess what I thought the current was going to do. And so now I need to be consistent to this drawing. And I can go in the backwards direction or in the forward direction, but I would just generally go in the forward direction as much as I possibly can. But I am going to, for sure, choose to go backwards through one of these batteries so that we can see how the rules play out. So let's take the left loop as our first one. I have three voltages, three places where the voltage changes. One in the battery, this resistor, and this resistor. So I'm going to follow through here, down through I3, come back together, a split I should say, into I1 and come back this way. So three voltage changes. Remember, that says that 0 should be equal to 12 because I'm going in the direction of the current through the battery minus 10 I1 minus, I'm going to go in the direction of I3. I3 is 5 ohms, 5 I3. Okay, nice simple equation, but at this point right now, unsolvable because I don't even have another connection to I2. So somehow I need to bring I2 into it. Now I could follow this one, and to be honest with you, that would be the smarter choice. It would be smarter probably to just choose this one. It's a little bit easier for us to work with. But instead, I'm going to choose the big loop. I'm going to go all the way around the entire circuit, starting back here at this exact same place. So 12 minus 10 I1, but this time let's continue forward. I'm going backwards to what I'm saying the current was doing, what the current was doing right there. So that is going to be plus 15 I2. And then we're going backwards through the battery, so rather than a voltage increase, that would be a voltage decrease. Okay, so there's a little bit of cleaning up to do. So, essentially what we're going to do is we're going to work with these two equations. I'm going to clean up as much as I can. At some point, I'm going to bring this guy in to eliminate one of the variables, but let's get these guys cleaned up a little bit so we can see what we have actually here. So this is going to be 12 minus 10, I1 minus 5 I3, and this one is 7 minus 10 I1 plus 15 I2. All right, so it seems like probably the easiest thing to do is I actually have an equation for I3 that says that I3 is equal to I1 plus I2. So if you notice, if I make this substitution, then we will eliminate I3. So now I'll have an equation which has no I3 in it at all, And that's going to allow me to get down to two variables. And since I will have two equations, I can just finish those two equations like that. So let's go ahead and make that substitution, and let's get this thing sorted out. So 0 is equal to 12 minus 10 I1 minus, so now it's going to be 5 times I1 minus 5 times I2. And then this guy is 0, 10 I1, we're doing plus 15 I2. All right, so clearly these two guys are going to come together. So that's going to become minus 15 I1 and minus 5 I2. So that's minus 15 I1 minus 5 I2. 0 is 7 minus 10 I1 plus 15 I2. Okay, so at this point we want to eliminate one of the other variables. And to me, it would seem like the easiest one to probably eliminate is going to be this one, because I can see that all I need to do is multiply the top equation by 3. And once I multiply that equation by 3, then I'll be able to actually just add the two equations together, and I2 will just disappear. So all I'm going to do is take this equation times 3, and I'm going to drop it down here underneath. Okay, so I'm going to repeat this equation, but I'm going to flip it down underneath here just so that we don't have to keep rewriting everything. So that's going to be 0 is equal to 36 minus 45 I1 minus 15 I2. So now we can go ahead and add these two guys together, and that says 0 is equal to 7 plus 36 is going to be 43. And we have minus 10, and minus 45 is minus 55 I1. And now we can go ahead and solve this equation. So this says that 55 I1 is equal to 43, so I1 would be equal to 43 divided by 55 is 0.78. We'll say 0.782 amps. Okay, so obviously at this point, what we'd want to do is start working our way back through the equations. The last one we'll get by going back all the way to the very first equation where we said that the current was going to be equal to I1 plus I2 equals I3. Now, if at any point you get a current that is negative, the meaning of that is that you picked the wrong direction back here. So if we did pick the wrong direction for I2, we will know about it because the current will come out to be a negative answer, and that will reveal that everything was right, but we just picked the wrong direction for that current. So at this point, where I would probably go is I would probably go back to, really we can do any one of these two equations. I would probably go back to this one right there. So I'm going to bring this back up to there and put this right here. So 0 is equal to 12 minus 15 times 0.782 minus 5 I2. All right, so let me clean up this portion right here. So that's going to be 12 minus 15 times 0.782. That's equal to 0.27. And I'm going to bring this guy over to the other side. So 5I2 is equal to 0.27. And so I can see already that I2 is going to come out to be positive. So that would indicate that we did pick the right direction, but that there was not very much current that was going through this guy, because 0.27 divided by 5 is equal to 0.054 amps. That's I2. Last step is bring these two guys together. I3 equals 0.054 plus 0.782 plus 0.782 is equal to 0.836. Now, on the IB exam, it should be hopefully very apparent that you would never be asked to do something. I mean, just look how elaborate this was. And this was a pretty simple circuit, right? I mean, I could have taken one more resistor out, but this is not a very complicated circuit overall. And so you're really being asked to just understand it conceptually, it seems to me. It's oftentimes in the multiple choice question, honestly. And so they'll look to see, like, do you know how to set up this equation? This is what we really need to practice doing. So we're going to look at just a few examples of this. And really, we won't need to necessarily go through the entire math, but we do want to make sure that we could set up the circuit correctly and that you understand how to apply the rules. And then it's very unlikely they're going to ask you to follow all the way through, because even the simplest circuit is going to require quite a bit of math and not a lot of physics. So it's really more about understanding these conceptual things that we did up here and where does this come from. That's definitely very relevant. Would be a great question for them to ask about, why is this rule? Why does Kirchhoff's rule, or what's the underlying principle? And the law of conservation of charge and energy are the conceptual underpinnings of these rules. So that's the way that we'll approach Kirchhoff's rules.